All right, Kevin Leach here for the compilers class. There was a number of requests to have a video guide posted for a Python-based PA4 implementation, and that's reasonable. So I'll be doing that probably over the course of multiple videos um, to help get you started. Between my notes and my memory of the assignments, we will be able to come up with something. Um, so first. I wanted to start by giving sort of an overview of what PA4 is. Because you have only 2 weeks to do it. That's a pretty short amount of time. I want to make things as clear as possible with the logistics of the assignment itself. So, just as a reminder, PA4 is the semantic analyzer, or the type checker for cool. In this assignment, you are assuming that your input is an abstract syntax tree. You have successfully parsed a cool program, the program is guaranteed to be structurally valid, right? So you can assume that we won't be giving you any malformed abstract syntax trees. All the input that you get is a structurally valid cool program, and your job is to take that tree and analyze the semantics of it. So not just looking at its semantic validity, or not just looking at its structural or syntactic validity, but now ensuring its semantic validity as well. Okay, so your job is to take one of these CLAST files that you've produced in PA3 and produce a CL type file, which is a cool annotated abstract syntax tree and some other fluff that is the result of a successful type checking. Now, as a reminder, the example I've used multiple times in the course is this idea of adding strings to integers. That's not a valid operation in cool. That doesn't make any sense. And so if we see something like that in the program, our job is to report it as a type checking error. And we'll talk about the formal basis for doing this sort of analysis in class. But for now in these videos, we'll take perhaps a more pragmatic approach and just um, think about things that make sense in the context of the cool language. Now, in addition to strings and integers and adding them together being type checking violations, there's also a starter list down here somewhere in this PA4 specification, right down here. So these include things like inheriting from the base classes like integer, like int bool, or inheriting from an undeclared class. A lot of these things are sort of natural and make a lot of sense. Your job is to implement something that enforces each of these rules. Now, this isn't an exhaustive list. We'll talk about how you might go about finding more examples of things to type check in just a minute during this video. Now, so one of the other things you might be confused about is PA4C versus PA4, and I want to spend some time clarifying that. So ultimately, the thing I will be grading is PA4, and that includes type checking everything. So be sure to turn this one in for the actual grade. PA4C, the checkpoint, we split up the types of checks that you might care to do into two broad categories. And for PA4C, the test cases that you're given for PA4C are everything except expression type checking. And so PA4C is basically about all of this stuff here, all the stuff listed here. Do you have a cycle in your type hierarchy? Do you inherit from a base class? That sort of stuff is included in PA4C. And so on the assignment submission website, you can explicitly submit to the PA4C. This isn't something that I'll be looking at for your grade, but if you're interested in splitting up which test cases are testing which part of your type checker, this is the way to do it. Basically, PA4C will only give you test cases that relate to type checking everything except expressions, and then PA4 adds a few more test cases that explicitly only goes after type checking expressions. Okay, so two broad categories. Feel free to use PA4C to your advantage to determine which test cases are explicitly related to expressions. All right. Now, let's see, for the output of PA4, it's specified here, the CL type file format. It's 4 parts, and we'll talk a little bit about each of those. First, we mentioned before the result of the type checker is to produce an annotated abstract syntax tree. Essentially, what it is the the tree that you produced in PA3, except that we annotate it now. Each of the nodes gets annotated with some type information, and that helps us make some guarantees about um, the intended execution, the intended behavior of the program. If we know something about the types, we can make some stronger guarantees about what the program's going to do when it finally executes. So the annotated abstract syntax tree is the AST, but we annotate it with some typing information. And now we also include these 3 other bits: the class map, implementation map, and parent map. And briefly, the class map and implementation map, these are ways of tracking all of the classes that have been defined in the program, as well as each class's attributes. So we care about knowing the names of attributes so we can potentially refer to them later when expressions refer to class attributes. So that's good to keep track of in this thing. We call it a class map. And then in the implementation map, we're basically keeping track of each method that is defined in each class. So the implementation map sort of tells us what does each method in each class look like, and what are the parameters associated with each of those methods. And so it's an explicit way to track globally scoped information about the program. You can the class map keeps track of attributes, so those are like the private fields, the data that make up a particular class. And then the implementation map is the list of methods inside of each class. These 2 will be useful later for when we get to code generation and laying out instances of classes in memory. Essentially, you want to be able to keep track explicitly of all the attributes because you need space for each of them when you're allocating a new object. And then you also want space for essentially a table of functions, so a V table. You'd have a list of function pointers, basically, a list of memory addresses that refer to functions. So this will come up later when we get to PA5. So it is a good exercise to have down now to explicitly think about the class and implementation maps. And then finally, the parent map helps us track inheritance relationships. This is essentially the same format that you saw for PA1. It's a graph described with edges. So you have pairs of lines. The pairs of lines refer to like one class, and then the second class is the thing that's the parent of the first class. Right, so we have so right here the child class, and then on the next line is that child class's parent on right. So we have these pairs of lines. Essentially helps us create a graph. Really, it should be a tree representation of the inheritance relationship between all the classes. Right? So that's all of the pieces and high-level bits of PA4. Let's see. So I think that's it before moving on. Right. So lots of detail here. Of course, you can also use the reference compiler to give plenty of examples for what it's supposed to look like. All right. So I mentioned before that this list of things to type check for is not complete. We'll talk about some in class, but if you're wondering, if you're sort of looking at this and trying to think, well, what do I actually come up with besides this list? I would start by suggesting recall that we give you access to the reference compiler, which contains which as a resourceful student you should refer to in this course. And so we give you the reference compiler program, and inside the program we have implemented a type checker, which means that the reference compiler implements all of these type checking rules that we care about. So one of the things that you can do is look for string constants that are embedded inside the reference compiler binary. And so if this is an example of a string that's produced during a type checking error, I might look through the binary for such a string, and oh look, there's a couple of these string constants embedded in the middle of the program binary, and so I might look at all the strings, all of these constant strings, for hints as to the types of, as to the category of type checking rules I should be implementing. And indeed, you could just use the strings utility in Linux, which is potentially very illuminating. So I'll use strings and I'll pipe it into less. Basically, strings looks for normal, like ASCII string representations inside a big binary file. It's, some of it, in fact, most of it here is junk. But if we scroll down, if we look for arithmetic on, oh, look at this, a huge wealth, treasure chest, stockpile of information. So not only do we care about doing arithmetic on things that aren't ints, but we might say, oh look, we're doing an invalid comparison between two types, right? Maybe it doesn't make sense to compare two types. So maybe we're trying to create a binding called self in a case expression. That's curiously specific, but we might want to check for that. We're using self type as a case branch. Can't do that. That's not allowed. Empty blocks. So if we have to have at least one expression inside of a block, otherwise it's not allowed. Right. So there's a whole bunch of these sorts of strings that are inside of the reference compiler binary that should provide a solid list of the categories of type checking rules that we want you to implement for pa4. So there are quite a few of them. It's sort of up to you to decide which ones you want to implement. With respect to the AutoGrader's test suite. So your job is to find the combination of type checking rules that sort of maximize the number of past test cases, right? So be sure to use the reference compiler as a resource for yourself. Right now I'm going to split the video and get started with actually implementing in Python, getting started with pa4. So I'll see you in the next video.